Okay, problem 761 says in a geothermal power plant, the used geothermal water at 80 degrees C enters a 15 centimeter diameter and 400 meter long uninsulated pipe at a rate of 8.5 kilograms per second and leaves at 70 degrees C before being re-injected back to the ground. Windy air at 15 degrees C flows normal to the pipe. Disregarding radiation, determine the average wind velocity in kilometers per hour. All right. Okay, so what we have here is we have water, and it's going into this pipe, and the average temperature at this location, I'm going to call T in, and that's going to equal 80 degrees C, and it leaves at another temperature, T exit, and that is 70 degrees C. And what we're doing is the wind is causing convection to occur, so we're going to be losing some Q out of this pipe, right? Some heat transfer is going to occur where we're losing um, some energy into that airflow outside, okay? And we're given some other information. We know the diameter of this pipe is equal to 0.15 meters. We know the length of it is 400 meters. We know the mass flow rate of the water, m dot, is 8.5 kilograms a second. We also know, I think that's it. That's all we know. So this is what we know, and we're trying to find what that average, or what the wind velocity is, V infinity. This is V infinity. Okay? So we can determine how much heat transfer we've lost, or I mean how much heat we've transferred, I should say, to the air, because I have this pipe is an open system, and we recall for an open system that Q dot is equal to m dot times Cp times the temperature change. So we go from 80 down to 70. Okay, so this is the amount of energy that has been lost in the fluid, in the water, because it has lost 10 degrees. Okay, so that's equal to 8.5. We need the Cp of water. Well, let's get some water properties. Water properties, and I need to get this at some average temperature. Well, it's 80 in, 70 out. Let's look at 75 degrees C and come up with what my specific heat is. Well, my specific heat for water is 4,193 joules per kilogram Kelvin. Okay, so 4,193 times 80 minus 70. And now I have what the heat transfer rate is, Q dot, and that happens to be 3.564 times 10 to the 5 watts, right? So I know that I've lost that much energy in the water. That means that energy had to go into the air through convection, okay? So I can then say that that amount of Q dot, okay, the heat transfer rate then to the air is equal to Newton's law of cooling, is also equal to H times the surface area times Ts minus T infinity. Okay, so I'm going to need some more properties. Now I'm dealing with the heat transfer from the pipe surface to the air. So I need to get some air properties. And I always need to do this for these external flow problems, well, for the majority of them, at what we call the film temperature, okay, which is the surface area, the surface temperature of the pipe, or the average between the surface area, the surface temperature of the pipe and the free stream. So the surface temperature of the pipe, it goes from 80 to 70, so we'll just average that and say it's 75. So we have to add to that the temperature of the free stream, 15, divide by 2. That gives me the average between the two. So this is equal to 45 degrees C. Okay, so we look up the properties of air at 45 degrees C. We get the thermal conductivity, 0.02699 watts per meter Kelvin. We have kinematic viscosity, 1.75 times 10 to the minus 5 meters squared per second. And we have a Prandtl number equivalent to 0.7241. All right, so now we have all my properties. Let me go into Newton's law of cooling. Well, Q dot was 3.564 times 10 to the 5 watts. That has to equal H. I still don't know what that is yet. That's what I'm going to be able to solve for, because I know the surface area and I know the temperature difference. Well, my surface area of a tube is just pi times the diameter, 0.15, times the length, 400 meters, times the temperature difference. Well, the surface temperature, again, we're going to have that average value to be 75, and then I have to subtract from that my free stream, which is 15. So now this is one equation, one unknown. I can rearrange and solve for what my heat transfer coefficient is. H is 31.51 watts per meter squared Kelvin. All right, so now I know H. I can determine the Nusselt number because they are related through. The Nusselt number is just equal to H times D divided by K. Okay, so H was 31.51, D 0.15, K 0.02699, and this gives me 175.1. That's my Nusselt number. All right, now I have my Nusselt number, and I can look for, well, what are the experimental correlations for that Nusselt number? The Nusselt number for a cylinder that works over an entire range of Reynolds number is equal to 0.3 plus 0.62 times the Reynolds number to the 0.5 times the Prandtl number to the 1/3 divided by 1 plus 0.4 divided by the Prandtl number raised to the 2/3, and the whole denominator raised to the 1/4 times 1 plus Reynolds number to the 282,000 raised to the 5/8, and that whole term raised to the 4/5. Okay, so I can start to plug in some values here. My Nusselt number is 175.1 equals 0.3 plus 0.62 times the Reynolds number to the 0.5. The Prandtl number I know, that's 0.7241 raised to the 1/3 divided by 1 plus 0.4 divided by the Prandtl number, 0.7241, raised to the 2/3, all raised to the 1/4, times 1 plus the Reynolds number divided by 282,000, raised to the 5/8, all raised to the 4/5. Okay, so we have one equation, one unknown. This winds up having to be solved in an iterative fashion or with a guess and check. So let's guess and check on this guy. And if I do it correctly, what I would find is that my Reynolds number through this equation is equal to 71,900. So the Reynolds number, the definition of that is V infinity times the diameter divided by the kinematic viscosity. So this is now equal to, well, V infinity, diameter I know, 0.15 divided by the viscosity, 1.75 times 10 to the minus 5. So now I have one equation, one unknown. I can solve for V infinity, and it happens to be 8.39 meters per second.